take you through the second part of this presentation, which is about the core neuron. I think now you are familiar with some aspects of the neuron, so I consider you are the expert users on the neuron side. So the second part is focus a bit on the technical aspects, in the sense that you will build the models with the neuron at certain point, and the models will become larger or more complex, and you want to run that bit efficiently on your laptop or on the your clusters that you have in your lab, or on the large supercomputers that we use via eBrain's infrastructure, or through the HBP infrastructures, or the other clusters that you have. So in this presentation, I try to give you an idea about, in order to run these neuron simulations efficiently, what are the ways that we are introducing into the neuron simulation toolchain, and the core neuron is the one way through which you can achieve this. So the brief agenda for this the second part is I will introduce the motivations, like why we started the core neuron and what that is, how you can get the models that you just learned through this first sections that you have. Robert demonstrated those through the eBrain's infrastructures, how you can get those models running through the core neuron library, what it involves in terms of changing either your hawk files or the mod file changes, and how you can run this simply on the eBrain. Show you a short demo. Obviously, when you do a complex simulations today, now you all aware of, there are now the different types of CPUs we have, there are GPUs, and we want to run our simulation fast, right? We don't want to wait for the simulations to run for days and weeks. Rather than, if you have a fast CPU or a fast GPU, you want to run that simulations faster. And I will just give you a brief let's say again, the guidelines about if you want to run simulations faster, what you can do, what you have to consider basically. Briefly, I will mention about just the NModel framework. That is another library that we are developing within the neuron ecosystem. So in case you are manipulating or playing with the mod files, there is some tool that we are developing that might help. And importantly, there's a lot of work that we are doing on neuron now to fundamentally improve the neuron. As Robert said, that we have developing this neuron simulator is being developed for last quite some time. Just 35 years, and we want to make sure that the whole ecosystem which is developed is maintainable and it's usable for the people, all the users. So I can briefly summarize what is going and how you can help. So let's get started. The motivations for core neuron, I don't want to repeat this, but Robert has already mentioned that neuron is there for a long time, like 35 years. And it is flexible simulation environment that you can use on Linux, Mac, Windows, basically every platform that typically we use in scientific computing community. You can do single cells or the complex network models on the desktop or larger supercomputers that we have. There's a Hawk Python. Here I mentioned the Hawk programming language. I think that Robert was hesitant to mention it because we want users to use a Python nowadays. But yeah, there are both scripting available, and there's interviews is a GUI component, and NModel is the channel description language. And there are many tools that people have built over the years or over the decades that use the neuron. So that's the background. But while today, if you see, there are the new computing systems that are around available through the eBrain's infrastructure, one of the questions as a neuron developers is how we can make sure that neuron is still relevant today on all computing infrastructures that is coming. So that involves, obviously, there are now the CPUs, there are GPUs. So everyone wants to run their simulations and, on the GPUs in order to run those faster. So we want to make sure that, okay, how neuron can be run on these new computing systems efficiently. It involves new programming models, like probably you might have heard people talk about the CUDA programming models or other programming models, OpenMP. And with this evolving software and hardware ecosystems, we have to make sure that our scientific softwares are continuously, improved and optimized So on the right-hand side, I just given examples of our own bluebrain file systems that we use at the bluebrain here, which involves like there are different types of CPUs. There are NVIDIA GPUs, and there is old generations of Intel Xeon Phi type of CPU type available there. And as a neuron simulator, I would say before a decade ago, we are mostly targeting CPU-based machines, and there were not that many GPUs available anyway. So you can use threads and processes to parallelizations, and it was working well. But today there is more than what is available, and we want to make sure that neuron works like in a performant way. The second part of this, the questions that we have is, people have developed large number of existing models, and how we make sure that those models still run efficiently. And Robert gave an example of the model DB, where we have now more than 800 models that are single cell or the large network models. There are a lot of channel descriptions that people have written over the last 30 years, and there are 6,000 mod files or thousands of unique mod files. And if you want to run something fast, it is not just easy to rewrite your models, in another simulator, because it involves the scripting, you have the input data formats, you have set up the validations, and just changing the simulator is not easy just for the performance reason. And we want to make sure that the users community that Neuron has developed over the last 35 years, they can run these models efficiently, and we want to make sure that Neuron is supporting those. And there is large, community that Neuron is using over last 3 decades. And people are also doing very large complex model. Just to showcase one of the examples that here we do at a bluebrain project, we build the large detailed morphologically detailed neuron models. This is one, what you see on the right-hand side is neocortex circuit with 9.3 million cells, with more than 3 billion compartments, with 145 billion synapses. And by just looking at the memory size of 170 terabyte, you can imagine that these models are huge. So we cannot simply simulate this on our small number of, like on not on the laptops, but not even on small number of compute nodes. We need a dedicated machines. And we want to make sure that Neuron can handle such large models efficiently and run at the speed, because we want to run this large simulations for different use cases, thus plasticity, and other people, want to exploit these models. So that's where the core neuron comes into the picture. We started this project 8, 9, 10 years ago almost, with the goals. Obviously, as I summarized, we want to make sure that Neuron runs on the new computing architectures to improve the performance. We want to make sure we can simulate the large networks, not necessarily in terms of the number of cells, but let's say you just have the detailed morphologically few single cells. We want to make sure that on your laptop also it can run in faster way with a smaller memory footprint. And at the same time, we want to be compatible with a neuron, so that people who are developing existing models, they basically can transparently use it. So that's basically is core neuron comes in. So the core neuron, we call it's a computing engine or library for the neuron to improve the performance and memory usage. To explicitly state that it's not a separate simulator or anything. It just, when you install Neuron today with some specific options, or by default, when you do pip install Neuron, the core neuron library is part of the Neuron, so it's there when you install Neuron, and even it will be, in the future, you will see that you will not probably hear the core neuron or something, because I will explain in the later slides, because the projects are merging. Internally, it uses the same numerical solvers as a neuron for the internal solvers in both in the mod files, or what neuron internal uses implicit Euler or other, the algorithms, they are exactly same. And we are using this at a bluebrain, all of our simulations, large scales, we do via core neuron library within the neuron, of course, because as I said, like the core neuron sits inside just neuron. And there are many use cases in the human brain project for the hippocampus detailed circuits that we build. They're also with core neuron. You can see that there are publications, or this everything is on bluebrain GitHub. Everything is open source. We are not going into the architectures or software architectures of the the components and so on, but the idea of showing you this architecture picture is that there is a neuron which has the Hawk, Python, and N model as the APIs, and you use that. And I know there are the users here that are building large and complex model. What core neuron brings is there is just small components that we add inside, and there is the N model is a new framework, and that sits inside this neuron ecosystems. And a user that you are using Hawk or Python API or N model or the mod files, you don't see that anything different, because as I explicitly stated, the core neuron is just library that we attach, and then you can switch that between neuron and core neuron. And I will show you the examples of that as well. So as a user, core neurons sit inside the neuron, and you don't explicitly see the difference. And I will show you the examples where you probably need to change things in either Python code or the mod files. So in a nutshell, what I want to say is Robert showed examples of how you can write the model. So I will not kind of go through the line by line here, but what we built in the previous session, that let's say you have existing neuron models where we do from neuron import H, we use the standard Hawk library, you create a sections, set the diameter, insert the HH channel in the soma, set the iClamp, and you are recording something in the soma, the voltage here, and you are doing standard init, and you're running the psol or continue run. So that's what you have your existing neuron model. And what we do is now, if you're building neuron from source, there's the extra options that you have to enable the core neuron. So today, when you are building with neuron from the source, we don't have this by default enable. That will change in the future. But if you do pip install the newer versions of neuron, it already brings the core neuron inbuilt into it. So that's all good. One thing that in the previous session, we didn't demonstrate, like how you build your own mod files. And I think some of neuron existing users, you already know that we described the mechanisms or channel dynamics into the mod files. And when you describe those inside the mod files, you have to compile those mod files so that neuron is aware of those mechanisms using NINIV model. That is a tool that is provided into the neuron. So you just do NINIV model and then dot or where your mod file directories are. The new options that we add is there is now -core neuron option that basically makes sure that mod files are also compiled for the core neuron library. So that is the one step you do. And next thing that you change into your model is you do now, there is a from neuron import core neuron. So that we ship now extra core neuron module inside it. You do core neuron.enable equal to true. That means now we enable core neuron. And now you do std init and psol after that. You run that your Python script, and now the things are going to just run into the core neuron library and efficiently. So this is basically an idea. I would say if in this whole presentation, another 15 minutes or 10 minutes I'm going to talk, the one slide I have to summarize this whole presentation would be like this one. So the idea of core neuron is you use the existing APIs or the programming methods that neuron provides that you are doing. So that you see here, we are building the models in the same way. You basically are using the, let's say, newer version of neuron from which we have the core neuron library support integrating. And when you can enable the simulations through the core neuron, and you can get that, simulations ready for the running on efficiently on CPU or GPU. So that's the main thing. There are in the next few slides, I'm going to talk about bit specific details about that. If you really want to, run this efficiently, obviously there are some considerations that you have to be aware of, and that I will talk into the next slides about these different aspects. I have to quickly show you an examples on eBrains. We have already shared with you the collab example, and Robert shared on the link. But if I have to show it here in the collab, there is a core neuron folder, the collab that we have created. And there is this first example, 0 simple HH core, simple HH. Robert basically introduced that example. What I have changed is I upgraded the neuron to the latest version rather than 8.0. And I just did pip show to make sure that I have the 8.2 release. Everything remains same. I think that you have already seen it. We are recording. And what here we are doing is importing core neuron. By default, its enable is false. Verbosity level I have set to 1. GPU is false as well, because this collab doesn't have the GPU simulations. And we are running this, the same. So this is the result. And there is no core neuron enable. I can set this to true, and I can run this now. As I have enabled verbosity level to 1 here, you can see some extra output, and the core neuron, this is basically core neuron output saying that, these are just extra detailed logs for us to know how many cells are there, how many compartments are there, and how much solver internally in core neuron is taking, and so on. But if you run then the results and everything remains same, So the idea would be what I explained in the slides, everything remains same, just with the few lines of the code. We want to enable the ability to run these models that you have been developing for the neuron to run on the CPUs or GPUs efficiently. So this is an example. Again, there are a few more examples I can refer to you, and there will be more examples that I will link into the resource sections. But I would say there is not much, to say in terms of the demonstrations, because if I will be demonstrating in terms of the changes, it will be more as these few lines of the changes where we are importing core neuron, and you can run then on the CPUs or GPUs that model efficiently. We'll come back to maybe another example later, but me go back to the slides so that we cover a few other details about what you need to be aware of. So that's basically the idea of the core neuron and so on. So if you have the models, how you can bring your large complex models to the core neuron. The inbuilt examples, inbuilt mechanisms that if you're using, as I have demonstrated, that you can just go and run, with the newer neuron. There are a few things that one needs to be aware of. The reason I am putting this some of technical details here, because I assume some of you are already building some complex models with neuron, and you will build in the future. And if you're considering about the performance aspects of these simulations, I want you to be aware of certain aspects. And that's where these slides, we have been getting some questions in the previous tutorials or through the issues. And I thought it would be a good idea to describe these aspects here. So the first thing people ask, okay, this is the core neuron library. It's already in the neuron. It's great. Okay, what we can actually run through the core neuron. So this brief explanation of that will be all spiking network simulations of single cell or networks of cells you can run today with a core neuron. If you have the gap junctions included, that you can do as well. And we support the fixed time step methods. But if you're using variable time step, for example, CVOD solvers, we are not currently supporting that. If you are using extracellular mechanisms or linear mechanisms, that we are not supporting. And Robert was explaining that one features of the neuron about the RxD module that ships with the neuron for quite some time, that we are not supporting with the core neuron. Things are changing in the future, or will change in the future, that will come back later at the end of this presentations. But this is what today you can do. And large number of network models that we do, or the people do, I would say that these features basically cover those. So those are the features where we kind of put a lot of efforts into it, supporting, and those you can run today. In terms of the Python or Hawk API, if you want to see what step-by-step you have to do, so this is basically one slide that will summarize. In that examples that I have mentioned, there is the first thing that neuron modules has a method called cache efficiency. This is a specific feature in the neuron that makes sure that the data that internally neuron you are creating, the sections, segments, synapses, or all basically objects, neuron can make sure that it organizes for the cache efficiency. This is how internally when simulation is executed, they are organized in some efficient manner so that the CPU can access the data efficiently and run simulation faster. So there's just that one method. Make sure that you are enabling that in top of your script somewhere before you do finalize. The second thing is, as I said, there is a core neuron module. Import that. Make sure to enable it with true. If you have GPUs on your laptop, and if you are using the right distribution of neuron, which has the GPU support, or you are building a neuron with a GPU support through the source code, so when you do cmake ... and enable core neuron, similarly, there is an enable GPU. We have documented that in the documentation. You can see that nrn.readthedocs.io. But if there is a GPU support, you can say GPU is equal to true. And the next option, cell permuted, just optimization flag. I will not go into here. You can look into the documentation, but you have to enable that. Verbosity flag is just for, you want to see different stats inside. It's not useful as a user, I would say. And then you have to do, std init or finalize is initialization, and then psolve now going to run your simulations with whatever configurations you do. So these are all, I would say, user-facing Python API changes that core neuron library brings. On the right-hand side, in case you still using the Hawk, or you have the model that is somehow written in Hawk for historical reasons, it's more or less the same thing that there's an Python method. I'm not that much familiar with the API, but Python allows you to execute the Python statements. So here, using Python wrapper, we say import core neuron, CVODE, just object we have created before. You can do that directly, cache efficient one. And with Python now, you can create a Python object, and through which you can access all the Python modules that neuron expose. So as we were doing from neuron import core neuron, through this Py object, you can do Py object core neuron enable equal to 1. And that's how you can, access the core neuron module through the Hawk interface. So more or less, I would say it's straightforward, nothing that much changed what we have seen. And this is more or less, I would say, what you will need if you have the Python or Hawk code and you want to port that into the neuron. So if there are no questions, feel free to interrupt me, but I will just get going, and then we can also discuss some things at the end if there are specific model questions. We will stay, a bit longer, if you want to discuss the details. One aspect is what needs to be changed into the mod files. This is answer could be just as easy as ideally nothing if the mod files are thread safe and you are up-to-date mod files and doesn't involve complicated verbatim blocks, which internally involves C API of neuron. This I'm mentioning that if you are the neuron new users, you will probably don't know what it means, the thread set mod files and what are the verbatim blocks. In this presentations, we will not go into the details of that. If you're existing neuron users, I think probably that what I'm talking about in terms of the complicated verbatim blocks, where neuron allows you to write even the C code inside the mod files if you have to do certain things that are not easily exposed into the mod files. because not everything can be described into the end model language, and people have been doing complicated things into the mod files that, depending upon the use cases, it's a good practice or bad practice, and we I don't want to comment too much on that, but just quick, I have to summarize that some practical examples of that. If you are writing mod files which involves the global state in the mod files, here is the one example where you are declaring some variables mnth to be a global. That means all this, the name of this is bad bit, the test. The test mechanism is going to use just a global property across all instances that you will have in different segments. It's going to have just only one value, m infinity. And here in this procedure, you can see that we are modifying that or accumulating or adding some to that variable. That is not good if we want to run these mechanisms in parallel, because you can imagine that on the CPUs or GPUs, when you want to run things faster, the way we do that faster is by running things in parallel. And on the GPUs or CPUs, to run things in parallel, usually you don't want to have a different threads of the GPUs to update the same values. And that's what we call the thread safety. There are different ways where you can still have the global state. Again, I don't want to go into the details, but this is one thing. If you are writing the mod files and if it has a global variables into it, and you want to run on the efficient way with core neuron, I think this is the one, the red flag that you have to fix. And here the fix is just, you can change this to the range, global to range, and then it's good. But this is something you should be aware of. The second example is if you have the complicated verbatim blocks. Here, this is example where we are doing the just C code inside this verbatim block. Instead of not going to the detail, I just showing obviously the part of the mod file. You have to make sure you tell to the neuron that whatever you are doing to that verbatim block is a thread safe. That neuron can assume that there is no any race conditions involved for this mod file. So you have to add a thread safe. There's one specific thing today about the table statements into the mod file. Briefly, if I have to say, if you're not familiar with what is the table statement is the way in the neuron you can pre-compute some values and you can use those values during the simulation so that you don't have to, the recompute things during the simulations. And you can set up some dependency that only if the Celsius is changed, then only recalculate m infinity and m tau. Because computing those is expensive. So these things today are not supported on the GPU. So you have to simply comment this line. This will be done automatically on the GPUs. But today, if you jump into the core neuron and want to run something on the GPU, I would say the table statements are not supported. You have to comment that out. The next major release of the neuron will fix that issue. But just to say that. Another two examples that I want to kind of warn you about is the random numbers usage, especially for synapses. This is examples, such kind of examples you will see in the mod files where we are using set RNG to set the random numbers. And it uses some verbatim blocks again. And typically you will find some examples which use the mcelran4, that is the old random number generator in the neuron. For quite some time, there is a random 1, 2, 3 that is being supported. So you have to make sure that you are using, the new random number generator for your synapses, random 1, 2, 3. And if you have this verbatim blocks needs to be adapted. The same thing about the pointers. If you're using pointers into the mod files and you are allocating your own data, those needs to be adapted. Now, this is again at very high level, right? Just in 15 minutes. But I just want to point out to this documentations into the neuron page where we have written about the mod file compatibility and how you can make your mod files compatible. Ideally, if you have mod files that are inherited or written in the nicer way for the newer neuron, probably you don't need to do anything. But we know that the people have been using the models that have been written over the decades from the model DB, and we reuse the mod files for the good reasons. And then sometime you have to make sure those mod files are adapted. I just want to point out there are already in this documentation, we point to the examples that we have been running through the core neuron, and we have been adapting those mod files that I have put here and also in this documentation. If you have the examples of certain synapse types, I would say go ahead, please go and check in these models for the showcase that we put together, because we have already might have done some work to adapt these representative mod files for the core neuron, and not necessarily only for core neuron, but to make this mod file thread safe when you want to use also the thread safety into the neuron. So this is just a list of some models. Take first look there rather than you trying to figure it out, or you can just come to the post this on the neuron GitHub page, and we'll be happy to assist you with that. A few notes about the performance considerations if you have to run faster. One thing just I want to mention here that some of the users here are the advanced users. You want to run this faster on the CPUs or GPUs. Pip install neuron is great, but note that if you want to use for any Python software that you install just via pip, not always those are efficient in terms of how they are built. Obviously, the popular software like NumPy, SciPy, obviously they have different mechanisms where those are optimized by default. But many scientific simulators, I would say, if you are doing pip install, you have to be a bit careful. And in case of the neuron, there are a few things. Core neuron, we relies on some vectorization thing. Again, you don't have to know about this now here. But I would say a summary from this is make sure to use the optimized compilers that typically you get on your clusters or supercomputers, or even today on the desktops. For example, you might be using some Intel CPUs or Intel, our laptops. There are Intel now ships the optimized compilers for a specific platform, and we just recommend for the neuron or with core neuron to use Intel compilers. This will change again in the newer version of the neuron release that we'll do sometime next year, but this is something to consider. If you're using pip install neuron, if you're compiling your mod files, then only it's okay to use this optimized compilers. So again, as an advanced user, you can just do CC equal to ICC and ICPC, and then do an NIV model, and the neuron will automatically use those optimized compilers to compile the mod file. Often for the complex model, this is where the time is spent for the simulations of this all mechanisms and synapse models are executed. So you want to at least make sure those are compiled. One specific aspect today in the core neuron I want to mention is there's model interactions that when you run something via neuron, so we have said h.continue run or psol. If you do that, neuron is executing the model. Once you enable the core neuron, and then do pc.psol, now the neuron is going to use internally, hand over that model to the core neuron to execute on CPU or GPU, right? And if you have done the GPU programming, you probably know that there is CPU and there is a GPU. We have to copy the model to the GPU, and then you execute. But imagine if you are doing this in loop, that you are calling the psol multiple times, a neuron is going to copy that model.
As multiplication, right? So from a biological perspective.
Sorry, there's something else. Yeah. So in terms of, if you're running this on GPU through a core neuron, you have to make sure that you are not like calling psols in multiple times, because the model will be copied to the GPU multiple times, and then you will not see the performance improvement if you are just copying the data back and forth between neuron and core neuron. So that is quickly just to mention that. I have mentioned this in the slides, so that just for the progress bar, for example, you should not stop the simulations multiple times. So this is what I think I have already kind of mentioned here. If you're running on the GPU, make sure to use in the documentations, we said there's NVIDIA HPC SDK through which you should build. Today, we also have the Neuron GPU nightly release that if you just pip install Neuron, we are not shipping the GPU support in the standard Neuron yet. There's a separate nightly GPU build that we are creating. This is bit in terms of the development release, I would say. It will come into the future version of Neuron bit officially, but I would say just make sure to install the Neuron with the right compilers if you really want to use GPUs. And just to get an idea of what you expect with this kind of efforts involved. So these are the recent publications models that we did in last few months ago, that on the Neuron, typically you see 4 to 5 or 6 improvements depending upon the CPU you get. But if you're running things on the GPUs, you can get the models, 20, 30, or 40 times improvements compared to if you're running just a Neuron on the CPU today on your laptops or on the HPC big supercomputers. And this is example of you can see olfactory bulb model. It's inside the Human Brain Project / olfactory bulb model. Everything on the GitHub. And this is another use case of the rat CA1 hippocampus model that is being developed by the community and that we have been regularly running on our machines, on the PISDINT and other HPP platforms that are also kind of using through the eBrains. So that's what you can install. One just quick thing, I don't want to go through this detail about the N model, but some of you are the Neuron users and being with the Neuron ecosystem for some time. If you are like using the mod files, or you want to analyze mod files, or you have to convert mod files or do something with the mod files, I want to say there is a new framework that we are developing. It's called the N-model compiler framework. You can just do pip install N-model, and it gives you the ability to analyze and manipulate the mod files for whatever reasons you want to do. You want to just extract the parameters, or you want to extract just ODEs that are used by the mod files, or you have to even convert the mod files to something else. You might ask why you want to do that, but I think some people in the past have tried that to write some parsers for the mod files. But we did this work ground up that you can use. And if anyone wants to do something with mod file and analyze something, I would say look there, because that is quite a comprehensive framework that we have put together. So in a summary, if I have to say, Core Neuron is an optimized library that we are developing within the Neuron ecosystem. Our goal is we want to enable all Neuron users to transparently use it with minimal or no modifications and get the benefit of improved performance on the new CPUs and GPUs that are coming up. This new N-model framework that we are developing that one can use to do anything with the mod files. So that's all about the Core Neuron. There are more fundamental changes coming into the Neuron, and I want to just summarize this as part of the Neuron project. So Neuron 9.0 and beyond, we are integrating, even at the source code level, everything that we have done into the Core Neuron. We are merging that into the Neuron source tree. So that's why I was saying probably you will not hear that much Core Neuron, because this all fundamental work that we have done is going into the Neuron. All the work that we have done over last decades, we are adopting that inside a Neuron itself. So that means we have done like optimized data structures that we do into the Core Neuron for efficient performance. We are now doing that work into Neuron itself. In terms of the memory duplications, and other features that we are doing, that we are all incorporating into the Neuron slowly. And there is a lot of work going on today. And at the same time, you can imagine that if any scientific software is developed for last 35 years, it has maintainability challenges and so on. And we want to make sure the code base remains modern and the features remains up to date, and the Neuron software is usable on any new Mac, Windows, or HPC systems. And that's why we are making sure that we are adopting the new programming languages from C++, rather than just traditionally it was C. The mod files are also being now translated to the C++. We are doing a lot of software engineering work to improve the error checking, reporting, improving the quality of the code, making sure that, yeah, like the error messages are up to, what it helps the end users and not, random errors that are not comprehensible. So all this is going today into the Neuron. There is a large number of people are working. If you want to see the resource, Robert has already pointed out, nr.readthedocs.io is the way where you should look at. Everything is on the GitHub. If you have any issues, there is a Neuron forum Robert has already mentioned, and there are other resources you can look at, if you want to see the details. Just quick shout out, we meet as part of the Neuron developers community every month. If you have any questions about the Neuron, or if you're interested to contributing to the Neuron, or if you are developing any tools based on Neuron, or if you simply would like to test new functionality in your models and provide a feedback, we have this fix every third Friday of the month. We meet for an hour. You can see that on the wiki of the Neuron simulator on the GitHub. Just ask any one of us, and we can add you to this meeting invitations and share the Zoom link. We also have the more developer-oriented or advanced user-oriented Slack channel. You can also join that. Just ask us. So with that, if you are interested in any work that we do, obviously, we are looking for good people, both on scientific side and on engineering side. Feel free to look at that. And with that, I will stop here.